We're going to finish this section that we were on. I don't remember what section it is, but solubility, we were talking about how ionic compounds dissolve. And we talked about how the polyatomic ions stay intact, and we also talked about how things like silver chloride do not dissolve in water. And so that brings up the topic of solubility. We say a compound is soluble if it dissolves in whatever liquid we're talking about. Usually it's water, but there are other solvents as well. We say it's insoluble if it does not dissolve. So how do we know if an ionic compound is soluble or not soluble, insoluble? Well, there's a list of rules that have been derived from experiments and observations, mixing things and seeing, does that dissolve? Does this dissolve? What's the pattern going on here? And so we're going to learn how to use this table of solubility rules. So let's look at this. On the top part, it lists ions that are generally soluble. Compounds containing these ions are mostly soluble. There are some exceptions. Now, for these first two, there are no exceptions, the first two rows. But here with chloride, bromide, iodide, if you have one of these ions paired with silver, Hg2, 2+, or lead 2+, then that compound is insoluble. So the exceptions are listed on the right column, and the general rule is listed on the left. So these guys are generally soluble except for these situations. In the lower part of the table, these are generally insoluble except for over here. I'm not going to make you memorize this table. I'll give it to you on an exam if you need it. Okay? But you need to know how to use it. And you're going to be referring to it a lot as you do the homework and things for lab and for this chapter.
Is C2H3O2 negative on the top, and then it says Ci negative, is that all one thing, or is there like a comma that it doesn't show there?
C2, which one?
This C2H3O2 negative, and then Cl negative, so those are separate?
Right, this is one row, and this is the second row, and this is the third row. So this is a different group with different exceptions.
Okay.
This is acetate.
Different rows. So the exceptions only go for that bottom Cl negative Br.
Right,
okay.
Yeah, it's not super clear. Let's make it super clear. I can do that.
Okay.
We'll use red. Okay, so these guys have no exceptions. These guys have no exceptions. And this part here goes for those guys.
Oh, okay.
And this goes for these guys.
That makes more sense.
That's better?
Yeah.
And so down here, that's for those guys. And that's also related to those ones on the top. And then this guy in the bottom is for those. Yeah, not the best table. If I was writing the book, I'd do it differently. I don't have time to write a book. Yeah, aqueous. So if we have it mixed with water, then we have to consult the table of solubility rules to determine whether it's going to be aqueous or a solid. Like silver chloride, you can put it in water, but it's still going to stay a solid. It's not going to dissolve. But if you have sodium chloride, it will dissolve, and so the state would be aqueous.
And you always use water for what it dissolves in?
Not always, no. But that table is for things dissolved in water.
That's just because the bonds between the ions stronger than that of the water.
It has to do with the strength of the bonds. There's an attraction between the positive and the negative ions in the ionic compound, and there's also an attraction between those ions and the water molecules, and then there's also attraction between the molecules of water for each other. And so whether a compound dissolves or not has to do with a balance of those three factors.
Is there any way of determining this besides just looking at the chart?
Not really, not really. You could calculate lattice energies and all kinds of crazy stuff like that, but looking at the chart is actually the simplest, most straightforward way to predict solubility.
Does the heat of the water increase solubility?
Yes, and we'll talk about that when we get to solutions, but yes, if the liquid is warmer, if the water is warmer, the solubility will increase. The solubility is dependent on temperature. And so right now we're talking qualitatively about soluble, saying, well, this dissolves or this doesn't dissolve. But later we'll talk a little bit about, well, how much of it will dissolve. Because with sodium chloride, I mean, you add a teaspoon of sodium chloride to a glass of water, and it will dissolve. If you keep adding salt, eventually you'll get to a point where no more will dissolve. And it's saturated, and that's the solubility limit. That solubility limit is temperature dependent. More will dissolve at a hotter temperature, and less will dissolve at a colder temperature.
Those are the energized state of
It has to do with the relationships of energy, and the attractive forces and stuff between the molecules. You guys ask really good questions. So let's look at this example. Determine whether each compound is soluble or insoluble. And I keep forgetting I don't want to just, well, maybe I'll have to do that. Okay, so CUS. So then just hold that in your head. CUS, and then let's go look at the table. So up here we're looking for copper ion or sulfide ion. And we look through there, we don't see it. Okay, so we come down here. Oh, look, there's sulfide. So sulfide compounds are mostly insoluble. That's what this is telling us. And then we look over here. Are there any exceptions? When it pairs with lithium, sodium, potassium, ammonium, that's not what we've got. When sulfide pairs with calcium, strontium, or barium, but that's not what we have. So this guy is insoluble. What color are we? Let's go with the white. So insoluble. FeSO4. So I'm going to go back to the table, and it's going to erase my thing, but that's okay. So again, we look through the top. Oh, SO4. Okay, SO4 2- is generally soluble, but then we have to go check to see if there are any exceptions. Strontium, barium, lead, calcium. Iron isn't listed. So that means, see, now it's gone. Oh well. That this one is soluble. Okay? So this is how we do it. So PbCO3. Got to go look in the table. Yeah, and so we see CO3 2-, that's the carbonate ion, is at the bottom, generally insoluble, except when it's with one of these guys, and it's not with one of these guys. So that means it's insoluble. So lead, oops.
And on the test we'll have that chart?
I'll
or
give you the
similar
chart, yeah.
Okay. So just learning how to read the chart.
It's learning how to read the chart, which, some people are like, well, duh, and other people, it's just not clear to you how to read that chart, okay? And that doesn't mean you're stupid, it just means that maybe you weren't taught how to read charts in school, or maybe your brain just thinks a different way.
We put the lines on it like you drew in here?
No, but you can do the lines. I forgot what it was already. Ammonium chloride, NH4Cl. Is it soluble or insoluble? So we have to go look at the chart. Well, here we have ammonium. Ammonium compounds are generally soluble, no exceptions. So that one's soluble. So this is soluble. Okay? Yes, question?
So will we ever be given elements that are not on that list?
I will not ask you to predict solubility of something that's not on the table. Yeah. There definitely are compounds that are not listed on the table, but I won't ask you to predict that. Yes?
So if the first compound is soluble and then the second is insoluble, that makes it all insoluble?
So if the first ion is soluble, but the second is insoluble, well, let's go back and look at that table. A situation that you could come up with that would be something like ammonium carbonate. where you look up here, and ammonium compounds are generally soluble with no exceptions. Carbonate compounds down here are generally insoluble, but then when we look at the exceptions, ammonium's listed. Okay, different books present these rules in different ways. Some of them just give you a list and they're in prioritized in order, and so if you just start at the top and you go until you find what you need and then that's it. This one is listing it a little bit differently. But you shouldn't come across a compound where it's telling you that it's soluble because of one ion without any exceptions, and it's insoluble because of the other. There shouldn't be any inconsistencies in the table. Any other questions?